All right, sharp on time. Good afternoon, everyone. Welcome again to AIM webinar series. So our today's topic is from prototype to production. We have some amazing speakers today. Our first speaker is Giridhar Raju. He is the founder of Apeiron Mobility, and he will take you through the design and manufacturing process from initial prototyping scribbles to generating files for a production job. Then we'll also have Richard Hammerl. He's the Autodesk technology electronic community specialist. He will also demonstrate how Fusion 360 provides all the tools to design electric circuit boards. Hi, Giridhar. So good to see you. Let me stop sharing my screen, and it's going to go to you. The show is all yours.
Awesome. So can I start?
Yes, please.
So hello, everybody. I'm sure there are a lot of people from around the world. Nice to meet you again. These are uncertain times. And so to start with, I'll talk about myself. I'm Giridhar from Apeiron Mobility, and I'm going to share my screen. Yeah. So the topic being prototype to production. How can somebody take their manufacturing process from prototype to say mass production? So all I'm going to do is I'm going to share my experience and what we have done at Apeiron Mobility. So at Apeiron Mobility, we build electric cargo bikes, and apart from that, we do a lot of battery packs. Right. So and I'm going to assume that a lot of the attendees or the people here are from either startup students or small groups trying to start on their own, and not anybody from say big OEMs. So to start with, I'm just going to say that at a stage where us as startups and companies are, I don't think there's a lot of difference between prototype and product. So in fact, if you look at our first iteration of the bike, that is this, and there is no. So this is our first prototype or our first product, right? There is not much of a difference. So we built this, we tested this thing, and we delivered it to the customers, right? And although we did tell the customers that this is the initial batch, there might be issues which we are going to fix. Right. So unless you are a Ford or a Tata Motors, wherein you the moment you give any part to customers, like you go in for a couple of $1 million worth of tooling, press tooling, molds, jigs, fixtures, and all that. I don't think there's a very hardcore difference between prototype and product, right? So we try to ship all the prototypes we build. So although we caution the customer and we handhold them through what could go wrong and if there's any support. So to start with, I would say to keep the time or the effort minimum between building a prototype, something that just you want to test the functionality of, and then something you can give to a customer. So I think it's the whole process starts the design phase itself. So in terms of when we start designing, we'll have to keep in mind what's the whole manufacturing process, as in how are we going to manufacture that at whatever scale we are. So for example, in the first batch of our bikes the first batch was 2 bikes, and then we did 10 bikes, and then we grew on from there. Same with our battery pack. Battery packs for 3-wheelers, right? So and the thing is none of these systems, right, the battery packs or the bike are tooled up. So I would say about 50 to 60% of the parts are off-the-shelf parts. You select. You go to your basic design, the foundational design. From there, you try to optimize the design so that you can accommodate as many off-the-shelf parts that you can, right? So that holds true for say things like wheels, wheel rims, brake systems, suspension systems, or displays and seating systems and things like that, right? And apart from that, we'll also have, while in design, be very cognizant of the processes that are available, right? So honestly, this whole assembly, right, there is not one single tool part. So this or this. So all of these have been made from systems that are production ready, but I would say prototyping parts like press brakes, laser cutting, and 3D printing. Significant amount of 3D printing that we use. and welding, right? So, and as of today, with tools like Fusion and AutoCAD, and it's significantly easier to be able to use prototype processes to be able to build production parts. For example, all these parts, so all the parts in here have been like, modeled, keeping in mind that we are going to laser cut them out of say 1.6 mm sheets or 2 mm sheets, and then weld them together, and then going to bend them in a press brake and then weld them together, right? So, but the important part is like you just have to use the features to the best. Like for example, and also to assemble this thing, so we don't use any fixture. There's not one single fixture that's used to assemble this thing. So, and how we are able to do that is, I'm just going to go to my Fusion screen.
Sure.
Let me open that up.
I think you have
can you
to
see my Fusion screen?
Yes.
Yeah. So, like, the best part is like these two. So, for example, like, these two are two different parts. And one of them is, so this is just a bent part, right? There's no complication. It's a, straightforward 1.6 mm steel sheet and then 120-degree bends. So there are 12 bends in this. So, but then how do we ensure that you can, so it's easy to do it in prototyping. So for example, when you are, say, want to make 1 or 2 parts, you can just sit with the manufacturer and say, yeah, this is the dimension I want. And then you, at each step, you go measuring that. And then, so it's a prototype, right? When you are assembling that, you can tweak here and there, say, use screws and stuff that tighten it up and then manage the tolerances. But, this current batch, as we speak, there are about 150 assemblies of these going on. So how do you ensure that, the quality stays and you get the same repeatability on the dimensions, right? So what it did was, so we added this member, right? And if you see the slots in here, so with whatever tolerances we allow, so these are two different parts, and then there are tolerances. So if and this is a straight cut part, so there is no way a laser cutting machine is going to miss on that, right? And the tolerances usually are up to 0.0201 mm, depending on how old the machine is and how good the operator is, right? So, and now if this part is, for example, cut and bent right, it will just go ahead and sit in these slots. So there are slots for each bend here. So, I mean, I would say, I don't want to use fancy words, but, I cannot find a better word. I would just say it's designed for assembly or manufacturability, right? I don't have to have a separate fixture to go ahead and assemble that, right? So, and we made these parts. And now once you do that, so how do you go ahead and make a full box out of that, right? So, and ensure and do that without any flex. So, I mean, there are 12 bends here, and then there are about 9 bends here, 10 bends here. And how do you ensure that? And these are 1.6 mm sheets, and the length between this part and this part is about 500 mm. And how do you ensure that they align up properly without any mess, right? And use the same slots at the corners, right? So if the part is assembled right, you just they just go and sit there in the respective slots. There's no way, I mean, the operator or the welder who is going to assemble this is going to mess this up, right? And similarly, like for all the parts, so same with the base plate that we do. So, right, and the most important part and the significant structural part is the base plate, right? So it's got 12 plates. This is going to take the whole load of, it's a 140 kg heavy assembly, and this is an automotive part. So it's got to take 30G shocks, and it's got to take 3G vibration loads for about 2 hours in each axis, right? So and we did the same. So like the base plate itself is 2 mm sheet, and it just bent. No complications, it just bent, but we just ensure that there are alignment holes, right? So these alignment holes, and you have similar slots on the base plates. Sorry, on the reinforcement bars, right? So this is one example of how you can ensure that you can take any product from your first prototype to production without investing significantly on tooling and taking time for that. So I would say that the biggest challenge for any product from prototype to production is the cost of tooling and the whole cost of fixturing the assemblies. So I think once you take care of these things while assembly, and if you are cognizant of how you're going to assemble this thing, and you can build the whole thing and in around that, right? So figure out what tools you have. So and we use significant amount of press brakes. CNC press brakes are quite accurate. I mean, you can get angles, close to 0.1, 0.2 degrees, and the dimensional accuracy is about, again, 0.5 is easily achievable. So, and ensure that the assembly has tolerance for such a offset, right? And also, you see, like, this is a structural part, and for shock loads of 30 dg on each axis, you have to ensure that these don't deform. So, and what we did for that is, so we have 3D printed spacers, and like we have a farm of about 4 3D printers, and they're almost running about at least 18 hours a day on a continuous basis, right? So, I mean, with 3D printing being so cheap nowadays, I think it's a no-brainer to be used in all kinds of manufacturing processes, right? And same with our bike. So when we did our bike, about I would say 8 to 10 kgs of plastic on the bike were 3D printed, I would say. And so I think you just have to, I'm not saying go for 3D printing for all parts. I mean, what I'm trying to say here is you'll have to take stock of what are the resources available with you, right? And then based on that, design your process, design your components that can be built on those systems, and they can be scaled, right? So, and it's a different case. Like it's the same with, like, for example, Prusa, right? So Prusa almost 3D prints 100% of the plastic parts on the printers, right? And it's a huge company. I mean, they sell about 1 million print. I mean, I would say about 100,000 printers so far overall, and most of the parts are 3D printed. All the plastic parts, at least, right? So, and I think that's the gist of it. And apart from that, I would say, while in the design process, you'll have to be extremely aware of what are the components available, and what are the products that are available in the market already that you can use ready-made. For example, bearings are standard, right? Linear rail guides, fixturing components, and things like that. In the automotive case, like you have a lot of suspension parts that are available standard. So, right, and the wheels, the tire patterns, handlebars, and displays, right? So we just have to try and ensure that you can leverage all those things to keep your tooling costs low and go to market as soon as possible. And the benefits of doing this is not just about keeping costs low, but then it helps you get to market faster, and iterate faster. So something like, if you can realize that something works or not extremely quickly because you have the parts available already, rather than you go full hog, do the tooling. Injection molding tools can be extremely expensive. And once you do the tooling and you figure out that either design changes or the customer requirement changes, or just the part just won't sit, right? These are extremely costly mistakes, and they can set you back in terms of go to market by about 2 to 3 months, right? And specifically with situations like now, the pandemic happening globally and suppliers not working full time, I mean, it can set you back by 6 to 9 months. You never know. Like specifically, there's a huge shortage of chips. So, I mean, I would, even want to focus on that right now, as in, like, the components that we designed with are not available in the market anymore, because, I mean, the lead time for that is about, 42, 52 weeks. And in that case, what do? Just go ahead and redesign that based on what chips are available in the market, right? So I think, and I don't have a lot of time here. I think Varun gave me strictly 15 minutes to talk. So I think I'm nearing that time.
All right.
And unless anybody has any questions, I'm back to Varun now.
Sure. Thank you so much, Giridhar. I see, I love the approach that you are actually using additive manufacturing in your end product and in improving your workflows. This is a very good thing. Only one question I have is, I see these small connectors attached to the assembly, the white one, which are
Yeah,
additively manufactured.
yeah.
What is the material that you're using?
This is ABS. So ours is automotive component, right? So we either we mostly use ABS or ASA.
Okay, because
Yeah.
when we tend to talk about Prusa, usually people are using PLA. I personally use that because this is
Okay.
fast through plate, but that's not convenient, I think.
Okay. So the problem with so printing ABS is like, you have issues with the wrapping and things like that, right? So the print just warps
Yes.
and it won't stick to the bed. So just have to. It's a bit of trial and error. So we, I mean, in our case, we have enclosures for all the printers, and ensure that the printer is printing at 100 degrees Celsius all the time. And the bed
Absolutely.
temperature is 110. You just tweak little parameters, and you should be able to get pretty good prints with ABS. I mean, personally, I love ABS. I mean, the way it prints, the strength, and a lot of times we we just print the part in ABS and then go ahead and machine that to get a better finish, or to certain forms
Totally.
that you cannot necessarily print strong enough.
Absolutely. Well, it's totally a great approach. You are using rapid prototyping techniques for your actual production job, that too in sheet metal and laser cutting.
Yeah.
So I think it's a good takeaway. I remember when I visited your facility in Bangalore, you were showing me one great big, like a variety of bikes, one yellow bike and all those things. Do you have anything to share on those lines, if that's not something sensitive?
I mean, yeah. So that's what I'm saying. So even with the bikes, even on the bikes front, I would say I didn't get enough time to run through the whole presentation, right? So I mean, the big question with a lot of small teams on a tight budget and startups is to tool or not to tool, right? So I mean, toolings can be extremely expensive. So if, for example, if I had to go ahead and tool for an assembly like this, it would easily take me about 40-50 lakhs, right? So, and I think for a startup where we are just trying to explore if the product even warrants an existence, or even if the customer wants the product, I mean, it's extremely difficult choice to be able to make in terms of, should we invest say 50-60 lakhs in a part or a tool that you're not sure what the outcome is going to be, right? So
Absolutely.
in that case, what you do is just build the prototype, right, and ensure that you can leverage whatever parts, whatever machining facilities or manufacturing facilities you have very easily, and leverage them to build your manufacturing, right? So, and as I said, I mean, I would never say it's a prototype. So most of the parts that we build, even the first assembly we built, we sold it to a customer. I mean, although we did one the customer that, so this is the first part we're building, that there might be challenges, there might be unexpected behavior, but we are here to take care of that, right? So and so most of the processes that we use are, I mean, CNC tube bending are available in any major city or any manufacturing facility, manufacturing setup around the globe, right? So press brakes are very common nowadays. And laser cutting is laser cutting, or water jet not as much, and laser cutting is extremely cheap, press brake is extremely cheap. CNC tube bending, you'll have to find the right partners. And I mean, for example, I'm in Bangalore, right? So I mean, we found about 8 manufacturers with CNC tube bending facilities, right? And all of them could do any different sets of radiuses or pipe diameters. And 3D printing is like, almost every other guy has a 3D
Right.
printer nowadays. And of course, like, go ahead and try to pick off the shelf parts that you can integrate right into the product, rather than going ahead and designing everything from scratch. It just takes too much time. And then, like, some parts that have been in the market essentially means that it has been tested, proven, and it does the job. It does not fail, so compared to where we might design the part and we might miss on critical factors like the heat treatment process or the coating process that might lead to the failure of the part, right?
Yeah.
I mean, I think it's a win-win. So in terms of, you keep your costs low, you have reliable, parts that have been tested in the market, and also like the time to market, the time to take it to the customer is extremely can be extremely short if you plan the whole process along with the design at the starting, right?
Totally. We have a very interesting question. I think we can conclude your presentation with that. What is the basic aim in prototype or product to be affordable or be the mass production ready for a startup?
Also, that's a very tricky question. Like you can never answer that. It depends on various factors in terms of how much cash can you afford for the tooling, right? And what is the quantity of what is scale of production you want to do? So you want to do 10 parts, you want to do 100 parts, 1,000 parts, or 10,000, a million parts, right? So the approach is going to be different for each of these scales, and the cost structure as well. So for example, if the same part that I was discussing, if I have to say do 100,000 parts, so the process that I'm doing is currently is going to be expensive and time consuming. In that case, I'll have to definitely invest in tooling. So, but then there's a validation that I'm going to be selling 100,000 parts every month, and I go to tooling at that scale rather than I'm doing 10 parts a month and I'm doing tooling. So while not being sure that it's going to scale or not.
Totally. The way I see this also is, I think whenever we design a prototype or something, I think we should all consider designing it as identical to the actual final outcome.
Absolutely.
Product, so that we maintain all the standards and processes.
Yeah.
Cool. All right. I think this is a good presentation. We are a little bit over time, and now let's quickly roll over to our next speaker, Richard. So guys, let me tell you, Richard is one of the core person from Autodesk Eagle team. You might have heard about the great PCB design solution, which is now also included in Fusion 360 electronics. So I so appreciate Richard taking time from Europe and giving his valuable inputs on how to design effective PCB design and circuitry using Fusion Electronics workspace. Hi, Richard. Thank you for joining.
Hi, Varun. Thank you for the introduction. Thank you for your invite. It's really great to be here and to show you a bit about electronics in Fusion. Yes, as you said, I've been with the Eagle team for a long time. It was back in 1994 when I joined CADsoft, and yes, it's my life companion. And yes, I would like to show a bit about what is the recent development and where do we go to. And just let me start with the presentation. If you're okay, Varun, then I simply start. Okay, so then let me share my screen. I hope it's the right one. Yes, and let's say share. You should see the first slide of my presentation here. It's something about we have electronics. Varun, you mentioned this. We have electronics in Fusion 360, and that's what we see as the future of electromechanical design. And yes. I just want to give you a bit of information, what we do, what are the design challenges. I have experienced a long time with Eagle, and I know how we worked 30 years ago and how the things changed recently. Of course, I would like to give a very short introduction of electronics in Fusion. The electronic part meets MCAD, and I would like to show you, I have prepared 2 short videos that give you an overview of what we can do in electronics. There would be a lot more we could talk about. We can have the next 5 hours if you want to. I just picked out a few topics. So talking about long time ago, I don't know how you, the audience now, is involved in electronics, but if you look back, let's say 30 years, it was not unusual that you draw your schematic on a sheet of paper, that you tried to bring your traces, the tracks, onto a full copper PCB using some pen and really drawing it, or using some symbols and try to rub them onto the copper board and do your electronics design, the printed circuit board. Well, you see on the top middle image, this was very short after the foundation of CADsoft. That's the very first Eagle version we presented on an exhibition in 1988 or something like this. So that's really the first Eagle. And if you go to the right bottom image, you see we have 3D, we have a 2D PCB. It's properly aligned on the computer. Of course, we do this. And of course, We want to have a 3D representation because we want to bring this product together into mechanics, electronics and mechanics. That's one part. And if you compare it to the mechanical world, there was a similar development. In the beginning, you drew everything on paper. I learned this in my studies. I started to draw on with big sheets of paper, construction plans and all this stuff. And then, of course, we got computers. Hello, 1986, that was the first AutoCAD version. And then it was black and white. Later, we have more sophisticated, more computer power. We have the inventor on the right-hand side. And now if we go to the right-hand side on bottom, you see the knife here, that's already in Fusion. And we can do animation, we can do simulation, we can do a lot of stuff in Fusion. So there's a big progress, and the progress is getting quicker and quicker. The steps from one to the next, it's always more and more shorter and shorter. So that's something we see. We increase the speed of our design tools we have. And that's the reason I would like to talk about the design challenges. What do you expect? What do you need as an engineer if you want to do electronics, if I want to do product design? I would like to have a design environment that meets both the electrical world and the mechanical world. Because do you know any product? Of course, there's some, but most products have electronics inside. And I also want to be sure that everybody works with the recent version. I want to be sure that all the functionality is there and that it works as I expect. And I collaborate. I want to work in a team, and I need to quickly respond to design changes, for example. If you go back, when I started with CADsoft and Eagle, do you know how we did technical support? We wrote letters. We put it into the mailbox and sent it to them. And so a support case took a week or two. And so that these times are gone. It's good that they're gone, but we need quick response. And that's why we bring electronics and mechanics under one hood into Fusion. And because we want to have an effective collaboration, we want to work together. Varun, you're in India. I'm here in Europe. Our colleagues, most of them are in the west coast of the US. So if we would work together directly, I can't simply take the phone and call you. I need a way to be efficient in collaboration. That's something we bring into one platform, and that's again Fusion. And of course, if you think back all the time, how do you exchange data? It's a file conversion. When I was in Eagle or any other CAD system or ECAD system, and I want to bring my ideas into the mechanics world, I export something, step file, a DXF file, whatever it is, and then I import it. And then you decide, okay, you have to do a change. I have a second version, a third version, a fourth version, and say, oh, the fourth version, that wasn't good. I have to use the third one. Then you send the third one to your guy who does the mechanics. He gets a lot of files, and it's hard to not do an error here. I've seen this very often. Say, okay, there's something wrong. Yeah, it's the wrong version you took. You have to take this one. And this costs a lot of time and money, and that's something we want to avoid. And the other thing is, we would like to have a functional 3D. So I don't only want to have an image of my PCB. I would like to use it. I would like to do a thermal simulation, as you see here in the top right image, for example. And that's something, yeah, we want to do with Fusion. So the reason, I think 5 years ago, Eagle was acquired or brought into Autodesk. And our first step was to make Eagle collaborate with Fusion. This was the first step. I want to have my 2D PCB, I want to create a 3D, and then I want to go on and do something with it, bring it into my product. And this was the first step. And there was a lot of development in the recent years. A lot of functionality came into Eagle. I don't want to mention all this stuff because this would much too much to tell you. There are a lot of new functionality in routing functions, guided routing, push and shove, a lot of improvement also in schematic, in library design. We have 3D models assigned. Yeah, and that's something now. That was the first step. And as I think since beginning of last year, 2020 in January, we have electronics in Fusion, what we call, Fusion 360 electronics, of course. And let me show you how the workflow now is. So I'm in Fusion and I start the electronics design. Now we go from bottom left to the right. And the first step typically is, of course, I would like to create my schematic. I have an idea and want to bring it onto paper, so to say. And therefore I need components. Fusion offers a lot of components for you, so you can use them, resistors, capacitors, all the stuff. You have access to all the libraries that have been made with Eagle 20 years, 30 years ago. So you have access to a big pool of libraries where you can also use library definitions from the web, so download them. And of course, you can create your own. And so you build just your schematic. And at any time, you can switch to number 2, to the 2D PCB. I simply go, okay, I say, click, I want to start with the PCB. That's one mouse click, and Electronics opens the 2D PCB editor, and you can start arranging your components. You can think about the geometry of the board, for example. Every change you do in the schematic is automatically transferred into the board, and vice versa, also the other way around. With schematic, you see, I could also do a SPICE simulation. If you're not aware of what it is, so you can simulate the functionality of your electronics design and see what happens if I switch on and have power on my signals, what happens in the signals. So you can evaluate, is it good or bad what I'm doing here? Will it work as expected or not? And yeah, so that it's also a part of electronics. If you're in the 2D PCB and you have done it, you thought about your geometry and so on, then of course you can export data for the board manufacturer. CAM processor, that's a part of electronics, creates Gerber data, Epsilon data. That's what your board manufacturer would use. And what I mentioned now, this is exactly what a classical or traditional ECAD tool would do. That's what you have. And now we are a step further. So at any time I can say, okay, I have my 2D PCB and I would like to make a 3D PCB out of it, because my aim is I would like to have my electronics in my product. So I want to see where does it fit and all this stuff. And so it's just a click and say, okay, go from 2D to 3D PCB. And actually the 3D PCB is the heart of our design process in Fusion, because here I can go for e-cooling, for example, or I could also bring my PCB into this, into the full assembly. You see here on it's number 4 here, bottom right. I say, okay, my printed circuit board is in my steering wheel in this case. So that's the basic workflow. And sorry, and you can do changes. So I could do changes in the 3D PCB and say, okay, there's a USB connector, it's the wrong place. It has to be repositioned. I could simply reposition it and it's transferred back into my 2D PCB, because I have to rearrange maybe the traces and all the stuff. So that's something I have to do a reroute. And that's all related. It's just a click. Let me show you a bit more in a minute. And the next step is that we have, yeah, I already mentioned it. We have the 3D PCB as the core in our design process. And from this 3D PCB, I can do an e-cooling and thermal simulation on the board, for example. I can use Fusion for rendering and get super nice images of my product. I can create milling data. So if I would like to mill a prototype, that's also possible. Of course, I can go into a manufacturing drawing, bring my board in, have a part list in this, in the manufacturing drawing. And of course, the main purpose or the main workflow would be going into the design workspace, bringing in my board into my enclosure, into my product. Not only one, there could be, of course, more boards. It's an assembly, and you bring everything into your assembly drawing. And one nice thing I mentioned in the beginning was about collaboration. And that's something I would like to show you. It's also really nice for electronics, because you could share your your project, your schematic, your board, your 3D PCB with others, with your colleagues, with your boss, with somebody from marketing, because you simply give them a link, and they even do not need Fusion to work with. They need not to know how they can use and open the files. You give them a link, they use the browser, look into this, they have access, you have the 3D, you can do some commenting, you can write some information there. So it's always up to date what I'll be seeing here. So if you do a change in your board, you save it again, you will always be up to date and everybody knows what's going on. And that's really a really nice environment. It's not nice, I don't find the right word. It's really amazing to work this way. And all we have is inside Fusion. It's one platform. There's one set of data. You don't have to convert anything. You just go into the schematic, into the board, into the 3D PCB, share it with your colleagues via Fusion Team so they can look into it with the browser, for example. Okay, so now let me show you a bit about the workflows. This, I mentioned it, there are basically two ways I think we're working. And finally, it's a mixture of both. So there's one, the PCB drives the geometry of the product. So going back and thinking about electronics, people designing the electronics, they know everything about the circuits. What they have to do, what are the parts I want to use, and what's exactly inside electronics. The enclosure, I don't care, that doesn't matter. So that's something we discussed very often here in Autodesk, for example, because I say electronics customer thinks totally different than a mechanical customer because he has totally different priorities. We think about electronics inside our PCB and the enclosure. That's not important. So that's what I know from our side, from the electronic side. But of course, it's also the other way around, because if you have a product designer, he wants to have a smooth appearance, it should look good. And then he says, okay, that's the product, and you have to bring in your electronics. So I don't care what's on your board, but it has to be this size, and you have this room. That's exactly what you have, nothing more. And then you have to, to try to bring this into the product. And actually, we have these two ways of working, and I think finally that's something it evolves in collaboration, and that's the reason why we do this in Fusion. And so let me go to this slide. Here, that's just an example, and now I would like to explain how this works. So that's a PCB in a steering wheel. That's something we just designed. It's not ready. That's so to say in progress, but I would like to use it. Here we see, for example, that's an electromotor for driving an e-vehicle. So it's mounted on one of the axes for each wheel. And what we like to do is, you see here, of course, on the back side, I have different connections and so on, and I need some electronics. So just let me switch off a few of the things here. And actually, you see, we did the first try. There is already a printed circuit board. Now you see it in a moment. Here it is, just as an idea. But we want to do a change. I would like actually to have another geometry of the board. And I have a sketch here inside, which describes the contour of the board. It's pretty easy to design. And I have simply to click Create 3D PCB, click here, and a new tab opens. No, just click here, start, select the profile. You could have one or more profiles. You can care about holes and so on. And then I say, okay. And now just a new tab opens and you see the 3D PCB, the shape, it's there. It's exactly how you designed it in the mechanical part. And now I save it. Okay, so just saving it, and let's go to the next thing. So that's the mechanical side. Now I'm on the electronics part, because I would like to design a schematic. Oh, please, I have to apologize. 3 components, that's not really a schematic, but just to show you how it would work. So that's my schematic. At any time, I can switch into the PCB. I click here, switch to PCB. It's the 2D PCB document. You see, here it opens. You see kind of template. It's a rectangular board. I move the components there. Of course, I can arrange them. I can start the routing. I can mirror them on the bottom side. I can, whatever you can think of. And of course, at any time, you ideally at the beginning of the design process, you get the contour from the mechanics part, from your mechanics colleague. And that's very simple. I save my board now. And now let me switch to the 3D PCB and show you how I bring it into the 2D PCB. That's one mouse click. So now it's 2 mouse clicks. I'm here in my 3D PCB, and now I choose link to 2D PCB. So that's the icon. I select which PCB, it's my multi-PCB, and simply say, okay, and it's linked, and it's inside. So the rectangle is replaced with the contour coming from the motor. Now, of course, I have to do some rearrangements, and you see the yellow message, the 2D and 3D PCB are out of sync. Why? Because I don't have the components on it. So I just click here, View 3D PCB, click on it, and now you see it's in real time. It takes about 2 seconds or 3, and then the board is populated. And so I can go back and forth. It's just switching the tabs from 2D PCB to 3D PCB. And there's even one step more in this last slide. I would like to show you. This is about edit in place. And here we're in a situation, I know it's very simple. I have an enclosure, and I have a PCB inside my inside my product, inside my enclosure. And now what I see, or what I can do, just let me start this. Go back. So here you see that's the 2D PCB linked to it. And now if you move it, you already see the opening for the USB connector is not at the right position. And I would like to change this. And I have 2 options. I can either edit the sketch here and simply move it to the right, to the correct position I would like to do, or I could also do an edit in place for the components for the electronics part. If you go here, you see the small pen, it's red and green, red and yellow. You click it, and so you enter the edit in place mode. And now I can click, move the component, rotate it, move it on the board, bring it on the right position. Of course, here it's done. I say, okay, save it, and it's transferred onto 3D PCB, and so it's back in 2D. You see here, I'm already on 2D PCB, and now I just want to move something on 2D PCB just to show you how this goes back. I save it, say view 3D PCB, go into the assembly, and now you see it takes some seconds. And now the components move. So that's basically the workflow we have. And of course, it's a very simple example. I could have shown you more sophisticated, but basically I think it's okay to see how we work. And it's really, as it's written here, it's just one tab away. So I go from 2D PCB into 3D. Changes, I go back and forth. I go into the assembly, I can do some changes, add it in place, and bring this back into the PCB. And everything under one hood. No file conversion. Easy collaboration. You see immediately if something happens in the 2D PCB or in the 3D PCB, you're always up to date. And that's what I wanted to show you. Thank you for your attention.
And really good best practices. Let's quickly jump to the Q&A. We are definitely over time, but we are seeing the love and the support from the participants in the chat box. So we have one question. Adityan asked this question: which 3D printer is good for printing automotive standard parts? I think Giridhar would be able to answer that.
So Varun, I think you are a better person to answer this than I am with your experience in 3D printing. So, but if you really want an answer from me, all I can say is it all depends on what kind of budget you have and what kind of scale you're looking at, right? So almost all 3D printers, any 3D printer with bed temperatures of 100 and above can print automotive grade parts, right? So it also depends on what material you want to print. You want maybe PETG, ABS, or ASU, or flexible parts. It depends on that. And then I think so there are a lot of comparisons online. I mean, and there's a new printer added almost every month. So there's always a printer selection guide depending on your budget and your features that you want. So I think there is I would not commit on a single model. But we personally use we have a fleet of about 4 Prusa printers, and we love that. They are so scalable. There's always support, and you can connect them to the cloud, as in like you can print from your PC, right? You don't have to just go and slot in the SD card each time. So we love Prusas, but there are other definitely better models. Good models, and it all depends on what budget you have.
Absolutely, I feel the same. It's hard to endorse one specific company for such kind of application, right? People have their own tastes and expectations. So as you mentioned, you are using Prusa, and that's an open source technique and a platform to design things. So it depends entirely upon your application and what you intend to do. But definitely I could say, see, I'm a PLA level person, and I use one Ultimaker and a Creality 3D printer. That's an open source kit. I use that. That's for my hobby purpose. But when it comes to printing part for automotive, I think the material plays a big role as compared to the machine.
True.
So that's what we have to consider. We have another question. This was asked by Sujin, and it was for Richard. Can we get the approximate machining time to manufacture the PCB in Fusion Workspace?
So you think of for milling it, or what's exactly the?
Yes, I think it's for milling.
I think, okay, to create the data, that's not a problem. The milling time, I think it can take about, depending of course of the complexity of the board, I would say it's between 20 minutes and an hour, maybe something like this. It's really depending. So if you put it onto the milling machine, number of drills. So it's hard to say, but it's something you do within an hour, or maybe 1.5 hours if it's more complex. So
I think the question is, can we get the machining time within the Fusion Workspace environment? Expected machining time.
It's a good question. I don't know.
The way we get in.
No, so we can. I would like to answer that. We can definitely get that with the CNC code, the GRBL code that we generate out of the Fusion. It will also give you how long it takes to cut the PCB or mill the PCB. So you can grade out of that. It's an easy thing. Yeah.
Yes.
Okay. Thank you. So I wasn't unsure if this is possible, but yeah. Okay. Thank you.
No problem.
We have one more question. Are there any resources available to master this PCB design workspace?
Yes, of course, we have a lot of resources there. So that means there's some samples in Fusion, and you can use the in-app help. So you could just go to help and look for Fusion Electronics. So there's the basics is all there. If you need more information, I think you should look onto one of our YouTube channels. We have a Fusion 360 YouTube channels. There's an electronics playlist that gives you a lot of information of features. It's from webinars where we start with a schematic, step by step, going to the PCB, creating manufacturing data and so on. And of course, also for certain topics about functions of how to route something, or how to create a library component, how to work with whatever it is, design rules and all the stuff. Yes, Fusion 360, Autodesk Fusion 360 electronics playlist. There you find a lot of content.
If you don't mind, I would like to add to that that the best thing with all the Fusion packages is that the amount of content available online, the amount of tutorials available online, that's immense. I mean, there is like there are tutorials, step-by-step tutorials for each and every small detail or small function. Supplied by Fusion or Autodesk itself. They have tutorial websites, blogs, apart from that YouTube, and apart from that, there's a huge user-created content. Like there are blogs, and even on YouTube there are a lot of hobbyists, detailing every step of any of the Fusion 360 process, be it mechanical or electronics or simulation and all those things. And that's the best part of working with Fusion.
Absolutely. I want to add to that. There's a ton of content available even on the website. And then we have a design academy where there are some self-learning courses. You can also get certification if you want. And adding to that, there is a ton of content created by the Fusion community itself. So all these things can be accessed. Anyhow, there are other websites also like Coursera and Udemy, and there are people who make courses on that. So that can also be used. Cool. All right. We are done for the questions. And so guys, next week, that's the last webinar for this webinar series. I forgot to change the name. It's going to be, this is going to be formulated product design. I mentioned it, modern machine shop. That's the old slide. So we'll have Green Design Tech. It's a Bangalore-based startup who makes electric vehicles again, but that's more on the commercial side. They have a very unique way of designing products. They call this process as formulated product design. And we'll have Karthik and Sundaram with us. He's the Chief Technology Officer, and he uses design modularity to create low-speed vehicles. And he claims that he has an approach that makes him faster than the competitors in industry. We'll also have Mickey Wakefield with us. He's the Autodesk Global Program Manager. He will showcase how Fusion reduces the total time required to switch from concept design to rapid prototyping stage. So feel free to go register yourself for this webinar. This is the last webinar. And we'll be also sharing all the recordings on the website itself. In case you haven't checked that, just go to the registration page, go back in the calendar. You'll be able to locate the watch now option. So this webinar is about to end, and I thank all the participants and the panelists for being here with us today. Thank you, Giridhar.
Thanks,
Thank you, Richard.
Our pleasure here.
Thank you, Anand.
Thank you, Varun. Thank you, Giridhar.
Thank you. Bye-bye.
Thank you,
All
Richard.
right, guys. Have a good day, and I see you next week. Thanks again.
See you.
Bye-bye.
Bye.
Bye.